everyone. My name is Elizabeth Kreitz. I'm a cryptographer at the Web3 Foundation. And today I'm going to be talking about some recent developments on multi-party Schnorr signatures. So just as a bit of an outline of this talk, I'm first going to cover some background on what secret keys are, what digital signatures are. I'm then going to talk specifically about Schnorr signatures and why we care about them. Then I'll also discuss why we care about multi-party versions of signature schemes and some recent developments for specifically multi-party Schnorr signatures. And then I'll talk about some new directions which will help guide some of the research in this space. So we'll start by talking about what a digital signature scheme is. But before we do that, we need to discuss what a cryptographic secret key is. So a secret key is some piece of information, it can be a string of numbers and letters, which secure digital communication. So in particular, a secret key might be used to decrypt some ciphertext or to sign a message. And I want to highlight already at this point that having a single secret key for one of these operations represents a single point of attack or failure. Now, a digital signature is like a digital analog of a pen and paper signature, and a pen and paper signature really testifies to the fact that you signed a particular message and that you were the person that signed that message. So in the digital world, again, a digital signature is used to verify that a message comes from a particular signer and that they hold the corresponding secret key. Digital signatures are ubiquitous, both in software and hardware. Sorry, I'm not sure why there's such a delay with the clicker. Okay. So the main security property for digital signatures is unforgeability. This is what we mean when we say that a signature scheme is secure or that we've proven that it's secure. And to begin with, for single-party signatures, unforgeability just means that an attacker cannot forge a signature. Is there somewhere I should be pointing it so that, okay. It's okay. Yeah. I think I have enough time anyway, even if it takes 10 more minutes just to get through the slides. So the message here can be some string, and the secret key is a field element. So there's also an additional secret value, which is sometimes called a nonce, which is a number used only once. So this is a number that a signer will use every time they sign a message. And the signature scheme consists of just two elements. So there's a group element R and a field element Z. And the group element R is a commitment to the nonce. So in a group, you have a generator G, and this capital R is just G raised to the little r. And the public key is the generator raised to the secret key. And the signature verification looks like this. So when you take as input a signature consisting of R and Z and a message, you check this equation. Again, the public key is the commitment to the secret key and the capital R commitment to the nonce. And you check it against the hash of all of the values, public key, message, and nonce. This is just to give you some idea of what the scheme looks like. I want to point out that it's very simple and only two elements are output. We won't really see the Schnorr signature scheme kind of technically for the rest of the talk, but yeah, this is just to highlight how simple it is, basically. Okay, the next question is, why do we care about Schnorr signatures in particular? So there are three signature schemes that are standardized by NIST, RSA, ECDSA, and Schnorr signatures. Now, RSA signatures are kind of a legacy signature system, and I would just want to point out that the signatures and the key sizes are quite large. So in particular, in comparison to a Schnorr or ECDSA signature, they're 6 times larger. But again, they are still pretty ubiquitous in cryptography. ECDSA was designed to get around the patent for Schnorr signatures. So Schnorr signatures were developed in 1991 and were patented until 2008. In the year 2000, NIST standardized ECDSA, but again, ECDSA is more complex than Schnorr. These additional complexities were literally added to get around the patent. And we'll see also later that the multi-party versions of ECDSA are even more complex. So Schnorr signatures were developed by Klaus-Peter Schnorr in 1991. As we've seen, it's a really clean, efficient scheme, and there's also quite a straightforward security proof for it. And in 2008, the patent expired. And we saw a bit of research in between, let's say, the year 2000 and the year 2018. There were a couple of threshold schemes, a couple of different variants of Schnorr. But in 2021, we saw a big shift in the cryptocurrency community with Bitcoin moving away from ECDSA signatures to Schnorr signatures. And we expect that there will be a lot of transition away from ECDSA to Schnorr, precisely because it's just simpler, it's efficient, it has these nice security proofs, and the multi-party versions are significantly cleaner. So given that there was a lot of interest in the cryptocurrency space for these threshold schemes, and in particular Schnorr schemes, NIST standardized Schnorr signatures in 2023. I would like to give honorable mention here to BLS. So BLS is not standardized by NIST. There was some effort around 2014, 2015. There was a bit of back and forth between industry partners kind of looking to NIST for something to use, and then NIST saying, well, we haven't standardized BLS, so nobody really came to any conclusion. But as we'll see with the threshold schemes, I think there should be more effort towards building a standardization for threshold BLS. BLS is used everywhere, also in cryptocurrencies. In particular, it's used for generating a good source of randomness in blockchain systems, but the verification is slow because it is a pairing-based scheme. Okay, so why do we care about multi-party Schnorr signatures in particular? As I pointed out in the beginning, cryptographic secret key is a single point of attack and failure. And if it's used for decrypting, signing, etc., the loss of theft or theft of it can have catastrophic consequences. So one idea is to take the secret key and to distribute it amongst a set of parties, where some of these parties may be corrupt. In particular, one type of multi-party threshold scheme is threshold signatures. So in a threshold signature scheme, there is a threshold T, and at least T parties are required to sign. There is a public key which represents all N signers, and the secret key that is distributed amongst the parties corresponds to that public key. But as long as T signers are involved in a signing session, a signature can be issued. But if fewer than T are participating, then no signature can be issued. So here we have a 2 out of 3 example. Another type of multi-party scheme is a multi-signature. So the difference here is that all N parties are required to sign. There still is a public key representing the set of parties, but it's important to note that it doesn't require any kind of secret sharing. So signing sets can kind of be formed on the fly. Parties can generate their own public keys and secret keys. So it's not really a subset of threshold signatures. You think, well, why would I use an N out of N scheme if I could use a T out of N? That seems more flexible. But again, there's a key generation mechanism that I'm not really talking about that can be quite complex. Multi-signatures are nice because they basically obviate the need for that. Some typical use cases for multi-party signatures, one I've mentioned, which is cryptocurrency wallets. So this would allow multiple parties to authorize a spend transaction. It can also be a way to distribute your key physically on different devices. I'd also like to mention that threshold signatures are being used to distribute certification authorities as well. So the properties that we're interested in multi-party Schnorr signing are as follows. One, we want it to produce a single signature. So in the past, Bitcoin for its multi-sig addresses was just taking in N signatures and verifying them individually and just saying, have some policy, these set of signers have participated, and now we just aggregate into the signature. But what we really want is for the signing for multiple parties to occur offline, and for the result of that to be a single signature that's posted on chain. This single signature should verify exactly like a standard single party Schnorr signature. So what's nice about this is that if you can build a scheme that does this, then it's backwards compatible with any scheme that uses standard single party Schnorr signatures. You can literally drop it in. We're also interested in schemes that are as efficient as possible. In particular, we're interested in schemes with a small number of signing rounds, ideally 2 or 3. It'd be great to have like a fully non-interactive scheme, but so far this doesn't exist for Schnorr, as we'll see. So now I will talk about some of the recent developments in the space of multi-party Schnorr signatures. When we talk about recent developments, really what I'm talking about is kind of the research that's been done from 2018 onwards. And this research has really centered around this issue of concurrent security. So I mentioned at the beginning, for regular standards signature scheme, we're interested in having the scheme be provably unforgeable. Well, what does it mean for a scheme to be unforgeable in the threshold setting? We're going to explore different notions of security. Concurrent security says that an attacker might be able to open many signing sessions at once. So these signing sessions could be with different signing sets on different messages, the same message, could even be with the same party in all signing sessions. And we want to say that the scheme is concurrently secure if an attacker still can't forge a signature, even with this added capability. Now, concurrent security is important, and there were a number of results recently that showed that tons of Schnorr multi-party schemes were broken in the concurrent setting. This last one in 2021 is a polynomial time attack. Some of you may have heard of these attacks. They're called RAWS attacks. And these types of attacks affected a number of schemes, so multi-signatures like the original Musig scheme, which was 2 rounds and now has to be 3 rounds. It also affected the original version of Frost, blind Schnorr signatures, and many, many more schemes. Now, an important caveat here is that a lot of these authors didn't claim concurrent security, so I think there were only 2 or 3 that actually claimed it. But again, concurrent security is really something important to capture because opening multiple signing sessions at once is a very real possibility. I will also say that one of these legacy schemes, Stinson and Strobel from 2001, which is a threshold Schnorr scheme, was not affected by these attacks. You might say, okay, great, we should have used that scheme, but it's multiple signing rounds because it uses key generation kind of within the signing protocol. So the rest of the schemes that I'm going to talk about now are really kind of from 2018 onwards, and they were built exactly to be secure in the concurrent setting. So everything that I mentioned here will be secure against RAWS attacks. And we have a number of 3-round schemes, starting with Musig. So again, Musig was originally a 2-round scheme. So in 2018, they altered it to be a 3-round scheme. We also have simple Musig, which is a slight variant of Musig, which uses proofs of possession. Then looking at some of the 2-round schemes, we have Musig 2, which was also concurrently built by my colleagues at Web3 Foundation, the DWMS scheme. And we also have Speedy Musig, which again is kind of a variant of Musig 2 with proofs of possession. Looking at some of the recent Schnorr threshold schemes, we have Simple Tsig, which has 2 online signing rounds and 1 offline signing round. We have the classic and zero Schnorr schemes, which have different security guarantees. There's also a scheme by Yehuda Lindell and Sparkle. And all of these kind of follow the same 3-round structure, which is essentially to commit and reveal. So the first 2 rounds are commit, reveal, and then produce a signature. So they all share a really similar structure. Looking at the 2-round schemes, we have schemes like Frost, Frost 2, Frost 3. These are very similar to the Musig 2 DWMS type schemes, but in the threshold setting. And you may be wondering what the differences are between these schemes. So Frost 2 was an optimization which reduced the number of exponentiations in signing from T, the threshold, to 1. And Frost 3 basically integrated 2 of the nonces. So it was kind of there was a big leap from Frost to Frost 2 and kind of a small leap from Frost 2 to Frost 3. I do want to point out that while I'm calling these schemes 2-round, they're really kind of partially non-interactive. So what this means is that the first round can be computed offline, and then there's just one online signing round, which is quite nice, and this may even be optimal. Now again, when we're talking about unforgeability of threshold signatures, I mentioned that we want to consider schemes that are secure in the concurrent setting. But we also want to consider the notion of liveness. This is really important for consensus systems where you need to produce a signature like every minute. And I want to point out that multi-signatures inherently do not guarantee liveness. So again, remember that a multi-signature requires all N parties to sign. So if one party goes offline, then no signature will be produced. Also, Frost is not robust. I think maybe there's, yeah, so robustness is kind of a subset of liveness where the protocol succeeds as long as T honest parties participate. So this would apply more to the threshold signatures, but is required for liveness. And schemes like Frost and most of the other schemes that I've shown are not robust. So what this means is that if a signer produces some partial signature that's garbage, it will get combined with an honest signature and the output will be garbage. Or the party could go offline. Now, there are ways to handle this. You can identify a party who's misbehaving, kick them out, and rerun with a different set of signers. This is kind of an inefficient process. It also requires some synchrony. So we are interested in schemes that achieve robustness in a more efficient way. So some recent developments in the robust space are Roast, which was in CCS 2022. And then we see a slew of schemes last year and very recently, Gross Shoop, Sprint, Hearts. So all of these do achieve robustness. These would be useful, I think, for consensus systems. You have large numbers of parties and it's really critical that you can output a signature. But I will mention that again, with schemes like Frost, we were kind of aiming for low communication rounds, and here we have a constant number of rounds. So in particular, there are some recent developments with schemes like MuSig2 and Frost. MuSig2 is being heavily incorporated into Bitcoin, so there's a number of people working at Blockstream. So as part of BIP 327, which integrates BIP 340, which moved from ECDSA to Schnorr, they're now incorporating MuSig2. And we also see some standardization efforts from Zcash. So Zcash also moved away from ECDSA to Schnorr. And as part of this ZIP 312, they are integrating Frost as part of their wallets. Very recently, Frost was standardized through the IRTF as well. And I just want to highlight a couple of different companies that are using Frost and MuSig2 in practice. So I mentioned, of course, that Bitcoin and Zcash are using them, but there's a number of others and even more recent ones that aren't even included on these slides. So we have like Cardano is also implementing MuSig2. Defense is really interested in Frost. I have a number of other people who come to me saying that they're interested in using these schemes. And a lot of what I've been talking about so far has kind of been 2018 to 2023, let's say. But what else are we thinking about? There are a couple of different types of security that we're interested in. So again, I mentioned around 2019, people were really interested in concurrent security. Now we're seeing a shift towards an additional property, which is called adaptive security. So what this means is that not only can an adversary open multiple signing sessions at once, but they can actually potentially corrupt parties kind of mid-signing. So there could be some signing party which is in session 1 and session 2, and in the first session they might be in signing round 1, the second session they might be in signing round 2, and at that point they become corrupted. Now, what does being corrupted mean? It means that the attacker learns that party's secret key, but also its state for everything that it's been doing so far. So the nonces it's been producing and all of the different signing sessions, et cetera. So this is a much, much stronger notion of security and also a lot harder to achieve. But it is becoming important through standardization efforts. People are interested in building schemes that satisfy this. I will say that Sparkle is the only scheme, so this is a 3-round threshold Schnorr, the only scheme currently that's been shown to achieve adaptive security and without secure erasure of secret state. So some schemes might be able to achieve adaptive security by basically deleting state immediately. So if the party gets corrupted, there's nothing there. But the problem with this is that secure erasure of secret state is really difficult to implement in practice. So we'd prefer to have schemes that achieve adaptive security even if the adversary can learn everything that the party has done so far. Another part of this research is I've been talking about threshold Schnorr schemes, and what I really mean is the probabilistic schemes. There is a version of Schnorr which is actually the standard in NIST called EDDSA. It's not verifiably deterministic, so it's basically the same as Schnorr in terms of verification is concerned. But we note that kind of the nonce in the probabilistic schemes is quite sensitive, this random value that's used to sign. So EDDSA is a nice way to develop the nonce based on the secret key and message in a deterministic way. And there have been a couple of schemes that have explored this, so in particular MuSig DN, and another scheme, and also there are schemes that are only secure for small numbers of parties. So again, there's a bit of a dichotomy here between small numbers of parties, large numbers of parties. In consensus, we kind of want robust schemes, right, where we always get a signature, but we might also be fine with small numbers of parties. So different schemes are satisfying different properties. It's not clear what is most useful overall. There might be different schemes for different applications. Also, I talked about sharing the secret key kind of being a critical component of all of these schemes, but I didn't talk about how you do that. So this is actually quite complex. There's a lot of research on distributed key generation protocols where the parties come together to form a joint secret. There's also trusted key generation, which can happen initially, and then the secret is gone and people just have shares. They never reconstruct the secret in any one place. But this is a whole active area of research that goes with multi-party Schnorr, but really is its own area altogether. And I will also point out that in people I've talked to who are implementing these schemes, this is really kind of the bottleneck. Like we have a lot of good implementations, the schemes are quite simple, but key generation is really where people are getting hung up because there's a lot of extra requirements on synchrony and things, broadcast channels, et cetera, which are more tricky to implement. So as far as new directions go, a lot of them are going to be dictated by this NIST call for multi-party schemes. So they're interested not just in signatures, but also encryption schemes, et cetera. This will come out in probably early 2025, and they are interested in standardizing schemes for the signature schemes that are currently standardized in the single party setting. So if we recall, we have RSA, ECDSA, and Schnorr. This seems to be getting worse over time. Does it let me go back? No? Can I just manually change these? There we go. So again, we have these three, and as far as threshold RSA goes, the state of the art in threshold RSA is a paper from 2006, and I will point out that it does achieve adaptive security. So I mentioned RSA signatures are really large compared to ECDSA and Schnorr, but they do have some nice properties. They achieve adaptive security, and also they're just a single signing round if all parties are honest. If all parties are not honest, then it's constant number of rounds. That's okay. Oh, yeah. So threshold ECDSA is more complex than threshold Schnorr. Again, ECDSA is already more complex than Schnorr, but if we just take a look at some of the security requirements for some of these schemes, these words don't need to mean anything to you, but it's just to show you kind of a list of assumptions that are used. So in particular, the Gennarodal scheme relies on the security of single-party ECDSA, the strong RSA assumption, the decisional Diffie-Hellman assumption, and the security of a non-malleable equivocable commitment scheme. The Canetti et al. Scheme relies also on the security of single-party ECDSA, strong RSA assumption, DDH, and the semantic security of PyA encryption, as well as the global random oracle model. So these are proved in a different type of security setting. And just to compare with the Schnorr schemes, these are all the schemes that you've seen today, they basically rely on two pretty standard assumptions. So one is the hardness of computing a discrete logarithm, and the other is computing the hardness of a sequence of discrete logarithms. So the one more discrete logarithm is a more, I would say it's a less conservative assumption, like discrete log is very standard, but also there's a lot of research that uses this assumption as well, and they all rely on the random oracle model. But these are just two assumptions versus kind of the 8 you see for the other schemes. Again, honorable mention to BLS. So threshold BLS is super simple. It's one round. You can also do threshold blind BLS in one round. So if you're looking for like the simplest scheme, really BLS is it. And I would like to point out that I'm part of the NIST submission team for Frost, along with my wonderful co-authors and colleagues and a number of implementers at Zcash and Electric Coin Company. And this is just to highlight that there are a consortium of researchers, both in industry and in academia, who are interested in these problems, in designing these schemes, improving the security, and it really takes a village to kind of put all of this together. And we will be submitting the scheme in early 2025. So just a couple of takeaways. Multi-party Schnorr signatures are being used everywhere in practice today, but there are still some challenges that remain. So again, the robust schemes are still multiple rounds. They don't have adaptive security. There are some other usability issues, but I'm really interested to hear if anyone in the audience is using these schemes, is interested in implementing them, what challenges you may have faced, things that went well, et cetera. Or if you just are interested in collaborating, learning more, I'm happy to talk with you. Thank you.